Hi, thank you so much for joining me. In this video, what we want to do is focus on overall thermodynamic favorability. And in kind of layman's term, that means a reaction under those conditions will proceed to make buckets of product at equilibrium. It would definitely be product favored situation. And a couple of people came up with a way to do this, and one person was Gibbs, came up with Gibbs free energy, hence why we have this as a delta G. And it's a balance of the enthalpy, which is the energy exchanged, and the entropy, that measure of freedom or disordered, or how much a system is dispersed. And one of the things I want you to note here is that temperature magnifies the entropy. And so if I have a favorable entropy, I'm going to want a high temperature. If I have an unfavorable entropy, I'll want a low temperature. So that's very important to wrap your mind around there. Okay, so what we're going to be doing is graphing delta G on our y-axis and temperature on the x-axis. This is just a very qualitative picture of what's going on in a system. So we're going to just set up possibilities between enthalpy and entropy. So if enthalpy is negative, that is considered a favorable process. And if entropy is positive, we have more freedom, more disorder, more ways of arranging, more microstates. That's also considered favorable. So what this means is under these conditions, there are no energy or entropy barriers to proceeding to make product. And what we find, if you look mathematically, if delta G naught is equal to a negative number, temperature is always positive because, of course, we would use Kelvin for temperature, so it would be positive. So we have minus a positive value. That means that delta G is always going to be a negative value. So delta G would be negative for what we call a thermodynamic favorable process. Thermodynamically favorable. Okay, that means that equilibrium products would be favored. All right, and I want you to notice here, as I said before, as we increased temperature, it became more and more favorable or negative because we are magnifying that favorable entropy here. So the increase in temperature magnified the favorable entropy. Okay, let's look at a next possibility. Enthalpy positive, that would represent an endothermic situation, and that's considered energetically unfavorable. That doesn't mean those reactions won't proceed. It just means we have a barrier for that reaction to proceed to make product. A negative entropy, that means we have less disorder, less freedom. That is also unfavorable. So now we have both barriers are unfavorable to proceed. And if we looked at the delta G, we'd have a positive minus a negative, and that would always be positive. So this would always be positive. It is never thermodynamically favorable. I'm just going to put a TF for thermodynamically favorable there. Okay? All right, and you notice that an increase in temperature made it less and less favorable because that increase in temperature always magnifies your entropy. And so it becomes less and less favorable. Okay, so those are kind of the two extremes. Always, so in this case, this was an always thermodynamically favorable. This is a never thermodynamically favorable. But there are two other possibilities that we want to explore. And that's when one is favorable and the other is unfavorable. And how can we overcome a barrier? for a reaction. So here we have a negative enthalpy. That's favorable. That's exothermic, and that's considered favorable. So we don't have an energy barrier here, but our entropy change is negative. So that's our barrier. That's unfavorable. So how can we overcome that? Well, it relies on temperature. If we can minimize the temperature, we can keep this factor small. And so at low temperatures, my favorable delta H would be, let's just look at magnitudes. My favorable delta H would be greater than...
Will the following students please come to the Counseling Center? Daniel Kim, Lily Stoppelbein, Zach Swartz, Caroline Sweat, Sarah Tanner. To the Counseling Center, please.
My unfavorable delta S. Okay, so at low temperatures, I can overcome that entropy barrier. At high temperatures, that unfavorable entropy will take over. So there's a name for this. When it is thermodynamically favorable at those low temperatures, we would say that it is enthalpy driven, because it was the favorable enthalpy that helped us overcome the process and make delta G not negative. All right, let's look at this situation. Here we have an unfavorable or endothermic delta H, but we have a favorable entropy. Okay, it's possible to overcome the unfavorable enthalpy if we increase our temperature to maximize that entropy. Okay, so it's now at high temperatures we can overcome that and have a thermodynamically favorable situation. And when that finally occurs, it's due to entropy. So we would say this was entropy driven. All right, understanding this equation is foundational to understanding thermodynamics. So make sure you wrap your minds around this, get the help of your peers or your instructor, and do your best job to get this qualitatively. And in another video, we'll talk about it quantitatively. Until then, at least for my kiddos, this is signing off.